Okay, guys, so what we're going to do now is we are going to observe a different statistic. So right now what we've done, we said we had p hat, right? And what we wanted to figure out, we did CLT for p hat. We also did confidence intervals. Okay, we did confidence intervals. And then we also did hypothesis testing. Okay. So that's what we did. So we did these three different things with p hat. Okay, now we're going to do exactly the same thing, but now with x bar. So remember, this was sample proportion, right? Sample proportion. Okay, and x bar is what do we call? Sample mean. Okay, so now what we want to figure out with the sample mean, we are going to do exactly the same thing. Find CLT. What is the central limit theorem for x bar say? Find a confidence interval, a CI, and a hypothesis test, HT. So we're going to do exactly the same thing with x bar. So with p hat, remember what we did it with the dice, right? So we were rolling the dice, trying to figure out if we had an even number, and then we, based on the how many even numbers we did, we got a p hat, and we graphed it on the board, and we got a normal distribution. Now, what is now the distribution of x bar now? What is x bar going to be? Is it still normal? What exactly is it? So let's try to investigate it. I don't know what x bar is, but I'm going to go ahead and figure it out. The way that we're going to do it is with this simulation, okay? So here it says the mean is 16, the median is 16, the standard deviation is equal to 5, okay? So notice this is our population, right? So we have an entire normal population, right? And what we're going to go ahead and do, we're going to take 5 samples, right? Take 5 samples and compute a mean, okay? So I'm going to go ahead and animate it so you guys can see we take 4 of them, right? Oh, I'm so sorry. 5 of them, right? We take all 5 of them, add them all together, and we get a mean, okay? And I'm going to go ahead and do this many, many different times. I'm going to take another 5 of them, and I get another mean. Do it again, take another 5, and then take another mean, okay? So it's basically the same thing that we were doing with proportions, right? But now I'm doing it for means, okay? So what do you think happens if I do this 10,000 times? If I do this 10,000 times, what is this general shape going to look like? Well, let's click on it. And what we get, surprise, surprise, it is a normal distribution, okay? Now, you must have probably thought, okay, well, it was already normal from the very beginning, so it makes sense for the means themselves to be normal also. Well, not necessarily. I can change this up, you know, to anything that I want, and I'm going to go ahead and do that. Now, some things to also take note. Notice that the mean of the initial one is the same thing as the mean of the means, okay? The means of the means. The only thing that's different is the standard deviation. The standard deviation is less spread. Here, you have a standard deviation of 5, right? Which is a little bit more spread than a standard deviation of 2. This is a little bit more condensed, okay? So now let's change the normal distribution to now maybe uniform, okay? So I change it to uniform, right? Are we still going to get the same normality? Well, let's see, okay? So I'm going to go ahead and animate. I'm going to get 5 of them, and then go ahead and compute a mean. I got all 5 of these. I'm going to add them all together, divide by 5, and get another mean. And I'm going to do this many, many different times. I could do it 5 more times, and I get that, right? When I do it 10,000 times, right, what I end up getting is somewhat of a normal distribution, okay? So I still get a normal distribution after I go ahead and do this many, many different times. The means, notice that they're basically the same, right? The means look almost around the same. The standard deviations, still, this one seems much less than this one, okay? Well, what happens if I were to do something different? So let's say I do a skewed distribution, okay? So now this one's skewed right, and I'm going to go ahead and get 5 samples, right? These are more likely to occur, right? So I'm going to get them, add them all together, divide by 5, and I get that. I'm going to do it again, do it many different times as much as I want to, right? And let's do this 10,000 times, okay? I do that, and notice that what I get is something that looks very normal. Not exactly normal, since it kind of looks like a little skewed over here, but I get something that's somewhat normal. So I can customize this any way that I want to. So also take note, the mean are basically the same, right? the standard deviation is still a little less, okay? I can make any old distribution that I want. I can customize it if I want, right? So I can maybe make a distribution that kind of looks like this. Let's say that that's what it looked like, right? So now what I'm going to do, I'm going to animate it one more time, get five of them, and compute a mean. And I'm going to do this many, many different times, 10,000 times. And what I get is, well, something that kind of looks normal, but not really, okay? The means, take note, kind of almost the same. Standard deviations, a little bit less than what it was before. Now, notice that it's not exactly normal. That's not kind of what we want to do. We can't use normal CDF on means, right? So we do know that it's going to be normal, but what happens when n gets really, really large? If I start increasing n to maybe 20, right? And we go ahead and compute this one more time, animate it, get 20 different observations from this parent function, right? And then once I get all 20 observations, add them all together and divide it by the total, right? I'm going to get some a mean. I'm going to do this 10,000 times, and we get something that looks very, very normal, right? So now it's much better as I increase the value of n. Okay, so what does this say? Okay, well, take note of what the mean was. The mean was originally 18, right? Mean is also 18.2 over, they look basically the same, and the standard deviation still kind of, right? So in the end, what we say is that x bar for sure is going to be normal. So when I take the original population, so here's the population, right? Here's the population. I sample, right? And I try to construct a distribution of my sample mean, okay? What we end up getting is a normal distribution, right? Now, the mean of the normal distribution, right, because we have to have a mean and we also have to have a standard deviation or standard error in this case, right? Well, what was the mean? Well, if we take note of all of the sample distributions that we got, the mean was exactly the same one as the original, right? Or approximately the same. So the mean of this is going to be equal to mu, okay? Mu being the population mean. Now, what is our standard error? Well, that one's a little bit different, right? It's a little bit harder to compute. If I go back, right, let's change this back to normal, right? And let's do this at 25, right? Well, we end up getting, and do this many, many different times, we get a normal distribution, of course. The means are exactly the same. Now, what about the standard deviations? Standard deviation here originally was 5. So the sigma, right, sigma here, let me go ahead and see if I can do this. It's not letting me do it. Okay, it's not letting me do it. Okay, so sigma here was 5. Okay, so sigma's 5. This population standard deviation was 5. Okay. Now here I have a 1. How did I get a 1? Well, let's go back to the, it seems to be dependent on the value of n. N is 25, right? So how can I get a 5 out from a 1? Well, it's going to be a little bit harder, but basically what it is you basically take sigma and you divide it by the square root of n. So this is equal to 5, sigma is equal to 5, the square root of whatever n is, right? So n, in this case, was 25, right? So let me go ahead and see if I can find an eraser, right? So 5 divided by 5, because the square root of 25 is 5, is going to give me 1, right? That's how they got that, okay? Now, do we really need to know that, or where this really formula came from? Not really. You just need to know how to use it. So the standard error is sigma over square root of n. Sorry. So let's go ahead and check this out. Here in summary, what did we find out? So here is a summarized version. So central limit theorem for means. So if you didn't get any of that simulation, that's okay, right? You can watch it again and try to figure it out one more time. That's a good thing about the videos, right? So here, the thing that we have is the central limit theorem for means, right? So what is the distribution of x bar? What does it look like? Well, n just means that it's normal distribution, right? X bar is normally distributed with a mean, right? So this is our mean, mu, and our standard deviation or standard error of sigma over square root of n, okay? All right, so the central limit theorem for mean says that regardless of whatever the distribution of the population was, so regardless if it was skewed or anything, right, as long as n is greater than 25, right, x bar is normal and has the mean of this and a standard deviation of sigma over square root of n. Okay, notice that I need to know what the population standard deviation is also from the very beginning. Okay, that is what the central limit theorem is. Okay, so to recap, x bar, as long as we know what that n is greater than 25, we know that x bar has a mean of mu and a standard error of sigma over square root of n. That's all it is. Okay, so this is all I want to talk about in this first video. So in the next video, I'm going to go ahead and do an example and show you where we use this. Okay.